engineer, there's a way to calculate exactly the damping force to get this. And this is Jordan Raffo did this for his extended essay. He looked at this thing, there's a differential equation there, and basically the friction force depends on the velocity, right? And so if we go back to this, look at the envelope of that. Isn't that kind of cool? Have you seen an envelope like that before? Yeah, was it like Newton's law of cooling? Yeah, the rate at which you lost something was proportional to how much you had, correct? So temperature, the rate at which the temperature dropped was proportional to the temperature that it was, correct? Right? This is not exactly, I don't think, a linear, like an exponential decay, but it's like that, isn't it? It's the same sort of thing, right? So it's an equation not unlike that. The amplitude is, what you do is you write an equation like this, right, where x equals x naught times e to the minus kt, right? That's your amplitude decays, and then it's sine omega t, right? It's something like that, but it might not be that exact same formula, right? So that's what he did, and he experimented with different size things, like the big ones damped down quickly, the small ones damped down more slowly, and he solved differential equations. He'll probably get a bad grade because the IB person who reads it won't understand the math. Be like, oh, I don't get this, F, you know, or something. No, I won't get an F, but it'll be like a cautious grade, a C. Ah, wasn't that good, you know? Okay, let's go back here. All right, so examples and things. We already looked at the resonance boxes, okay? How about a glass, right? My dad would have these big dinners, right? And he would, you know, we'd eat and then we'd talk and we'd sit at the dinner table for, honest to God, like hours after dinner. You know, there's dessert and there's great discussion. He was a college English professor, right? And one of the things we would do is we would have, like, he would serve us fruit juice and stuff in glasses like this. You know, a little orange juice, maybe a little grape juice or something like that. You know, apple juice maybe, right? And you would put your finger in. Isn't that cool? And if I add mass to it, what's it going to do? Ta-ta. Right, and we would tune them. We'd put stuff in there, different amounts of stuff in there, and tune it to certain things. We'd play chords and stuff. We have a very musical family, right? With no mass in there at all. That's kind of fun. And there were some really cool physics research projects that kids did where they looked at the mass of that, and they put different amounts of water in there, and they got a really, really pretty data for like how the volume affected the pitch, right? But anyway, there it is. Obviously, more mass makes it vibrate a bit slower, and less mass makes it vibrate a bit faster. Okay. How about the wiggler? Yes, sir.
Can you do that with just like any glass?
Yeah. No, it has to. The glass cup. The prerequisite is when you go like this, it's got to ring. It's got to be able to resonate, right? But if you can, yeah, then you can annoy people too with that, right? Okay. And then, of course, if I was a great opera singer and I could sing that note, right, and I could just, right, these things, you could increase the amplitude of that thing to the point where the glass might break, and that's the whole notion, and it really can happen. You really can do it. I can't sing that note, or I would, of course, show you this. You know, I also only have one glass, so you know, there it is. Here is this thing, and this is I call it my wiggler because in a high school classroom, if you say vibrator, you know, people, it's just all over, right? You just can't say that, right? Okay, but I'm going to turn this on, and it first is shaking very slowly. This thing, this whole post has a natural frequency, correct? But right now we are not matching that frequency, right? Yeah? Okay, so here we go. Are we ready for this? Watch the amplitude of the post. Are we getting there? Notice right now it's like we're not quite there, right? So I'm pumping energy in, right? And as I pump energy in, notice here's a funny thing. This is called phase coupling, right? As I pump energy in, it doesn't make the motor go faster. It just makes this thing go more gonzo. Watch. I think it's going to break, but maybe it won't. Oh, now we broke free. We now are going faster than the resonant frequency. So we're giving the motor more energy, but it's unavailable for this system because it's at the wrong frequency. Isn't that crazy? Right? But if I slow it down, watch it go through that regime again. Phase locking, turning it down, still turning it down, and it doesn't break out of the phase lock until now. Right? Now, have you ever... I'm still turning it up. Come on, baby, go. it breaks free. Okay. Now, examples of this explains a lot of things. My garbage disposal at home. You guys ever does your garbage disposal do this? You turn it on, and as it speeds up, it hits the resonant frequency of the countertop, and the countertop goes, right? And everything on the countertop shakes. You're nodding your head, yeah. And then it goes beyond that, and stuff quits shaking, right? Mine does that. It like goes through the space, so it ramps up, and then it hits the resonant frequency by which it can shake the countertop. The countertop goes, and the dishes move around kind of that I've got ready to rinse and stuff, and then it goes faster than that. Have you ever driven on a washboard road? Your car on a dirt road that has washboards in it? Yes? Yes. Okay. And you start going faster and faster, and as you hit the speed, there's a sweet spot for your speed where your car just goes nuts. Have you noticed that? Like your car's, honest to God, going to shake itself into smithereens. The way this happens is this. The way this happens is this. On the road, resonance explains so many things, right? Road graders come along. They make the road flat. Well, always there's some rock, like there's some little rock there, and really that rock is like, a glacial erratic, and they don't know it. So when they try to dig it up, right, it's like, but anyway, the road grader hits this, and it also, when it hits that, it makes a little thing like this, right? Yeah, it comes back down, the blade comes back down. And then the next car that comes along, if the road's totally smooth, it never gets started. But if there's just even one bump, and there's always one bump, right? Okay, the next car comes along, it goes up, it goes down, it hits here, and it makes a little bump there out of the gravel it dug out of here. The next car comes along, and since they're all going about the same speed, since they've all got the same, basically, cars with more mass have more springiness. Like, so trucks play this game too, passenger cars play the game, 15 passenger vans, everybody plays the game, right? Okay, they come along and they've all got about the same frequency, and what's moving is not the whole car, it's actually the undercarriage, the stuff attached to the wheels that moves with the wheels, right? Okay, and that goes up, the next car goes boom, hits this, goes down, makes a little divot there, makes a hill there, right? And so on and so forth, right? And these washboards get bigger and bigger and bigger, right? And as people go, it's just like this motor, right? As they try to go faster, they don't go faster. What happens? You're trying to go faster, you're pushing on the gas, and instead of going faster, your car does what? And everybody backs off at that point because they like their cars and they don't want to, right, destroy their car. Yeah? Yeah, this is just crazy. So what people do is they'll approach the speed from below and just sort of sit there at this thing. It's like, okay, I can tolerate that. But at this speed, you're going to go off the road, right? Your car is like never touching the ground hardly. It's just going, yeah, right? Okay. And you can actually go off the road. I mean, if the road goes around a corner when there's washboards and you're doing that just like crazy, your car will just go straight, just kind of like one of those, do you guys ever have those football games where the thing just shook and the little players moved around, electronic football? They're really retro, right? Okay, just like that, like, you can kind of move across there, right? So, okay, so I am driving to Chaco Canyon. Chaco Canyon has 23 miles of deeply washboarded roads. You can either go about 25 miles an hour, apparently 30 miles an hour, my Toyota Tercel hits the wall. And for a different car, it might be a different speed, right? 30 miles an hour is unacceptably slow, on a road that just goes like through sagebrush, dead straight, right? Way too slow, isn't it? So you can either go slower than 30 miles per hour, but in theory, if I've got the theory right, what's the other thing you could do? You can go faster, right? Let's look at this, let's look at this graph here, right? There's two places that are safe. Here's the amplitude of what your car is going to be doing. You can either go slower or faster. Now here's the problem with going faster normally, is that to go faster, you've got to go, you're approaching it from slower, and you've got to go through that regime, don't you? But what if there's a stretch of road, and there were these stretches, where they had paved the road. They paved it a good 50 yards before bridges and a good 50 yards after the bridges. And if the bridge is long, over a stream, well, that's quite a bit of space, isn't it? So what if when you hit one of those stretches that's paved, you really go through the gears and hit the next set of washboards at 60 miles per hour? Well, if you understand resonance, it's going to be okay. Yeah? You'll be okay. You'll be too fast for the car to resonate, and it'll just vibrate, but it won't resonate, right? And if you don't believe in resonance, if you just believe more speed will cause more vibration, then it's going to be Armageddon. The end of the universe as we know it, right? Because just subtle changes from 30 to 32 miles per hour cause, the car to just go apeshit, right? Okay?